Okay, for this video, we're going to finish up the last couple examples. So again, we are looking at the homework, or the worksheet. So with this first example, so a 10 kilogram pumpkin is moving horizontally at 5 meters at a constant velocity across a level floor using a horizontal force of 3 newtons. We want to know how much work is being done on the pumpkin. So when we look at our pumpkin here, we're just going to say this is our force applied, force of friction, force normal, and force of gravity. The big thing to keep in mind, since it is a constant velocity here, we know that our force normal and our force of gravity needs to be the same, and then our force of friction and our force applied need to be the same. So remember, if our velocity is constant, our acceleration is 0, and that means our net force is 0. That means everything cancels themselves out, which is a key thing for this. So when we go to look at this, we can use our work equals force applied times by distance. When we look at this, we are told that we are using 3.00 newtons of force on this. So 3.00 newtons times by our distance, which is 5 meters. And so we get 15.0 using significant figures. And then we're finding work, so it's going to be in joules. So there is our answer there. So again, the thing to keep in mind, we are using the applied force here. We will always use the applied force, not the net force. So we do not use the net force on these, because then we're doing no work on it, because the net force on this should be 0. Okay, let's look at the second example here. So we have a pineapple is held 1.2 meters above the floor for 5 seconds. How much work is being done on our pineapple? So again, we've got our person. Let me draw here. We've got our person here. Lovely drawing of our person. We have an even better drawing of our pineapple. So we go to look at our equation, work equals force times by distance. In all reality, we can go through and figure out how much force he's using. But the big thing is our distance here is 0 meters. We're not moving, we're just holding it there. So that's the big thing about reading through the problem and not jumping the gun. It's just held above it. So our distance is 0, so that means our work equals 0. You can either leave your answer just as 0, or you can say 0 joules. So if we have no distance, means no work. So that's nice and easy problem there, as long as you read it correctly. All right, next one. So we have a 50 kilogram banana box is pulled 11 meters along a level surface by a rope. If the rope makes an angle with the floor that is 35 degrees and the tension on the rope is 90 newtons, how much work is being done on the box? So this is where we start getting into using that second force equation. And I'm going to run out of room to draw here. So first off, let me try and draw this picture as best as possible. So we've got our banana box. It's being pulled up at a 35-degree angle. Like that's level with the floor. Pretend that it's level with the floor. So the formula we need to use is our force times by the cosine of 35 degrees, and please make sure your calculator's in degrees, not radians, times by our distance. So if we plug in our other numbers, our force, we're told the tension on the rope. So remember, tension is a force that deals with ropes and whatnot. That's going to be 90 times by the cosine of 35 times by our distance, which is 11. And you should get something pretty close to 811 joules. Again, plug it into your calculator. Make sure you're actually getting that number. So remember, use the component of the force that is in the same direction as the displacement. So basically what we did, switch colors here, is going back to trig. If this is our force, this is our angle, which is 35. Using cosine, we found the x component of it. We did not find the y. So we're only figuring out how much of that force is being applied straight out from it, is basically what you're doing. We will never use the sine on these, because sine would be finding how much force you're lifting up with. So with these, it's always going to be the cosine. All right, on our last example here, a 1,385 kilogram car is traveling at 61 kilometers an hour, and I'm going to stop right here, and I'm going to convert that. So remember, you need to divide this number by 3.6, and you get 16.9, and then 4 repeating, so we're just going to call it 16.9. Is brought to a stop while skidding 24 meters. We want to know how much work is being done on the car by friction. All right, but this has got a lot going on. So first off, our force body diagram. So since we're trying to come to a stop, if we're moving that direction, we're going to stop applying a force to keep moving forward. We're just trying to stop. So we're just using the force of friction to try and stop us. And then we have F normal and then force of gravity. So the only thing we're paying attention to is the force of friction. In order to do this, we need to know what our force is, the force of friction. So we need to know what our net force is. So we need to know what our mass and our acceleration is. We don't know what our acceleration is. We actually have to calculate this. This is going back to, I'll just switch to a different color, the big three. So VI, VF, A, delta X, and T. So we know our initial velocity, we're told, is 16.9. Our final should be 0 because we're coming to a stop. Acceleration is what we're looking for. Our distance stopping is 42, and we don't have time, so we don't need that one. So the formula we're going to use for this one is, sorry, I'm just going to figure out it right. Without doing stuff like that, VF squared equals VI squared plus 2A delta X. We know our final is 0. Our initial 16.9 squared plus 2A times by 42. What we end up getting when you solve for A, you should end up getting negative 3.42 meters per second squared. And yes, it should be negative because